related to this experiment, that is minor head loss measurements. Have you gone through it? Nobody is answering, so I assume that nobody has gone.
Sir, I have a doubt, sir, in that.
Yes, Naveen.
How it is independent of pressure, sir? The frictionless head loss. How it is?
Why friction loss head? Because that was major head loss you are talking first.
There are few factors, sir. How it is dependent on the velocity to the power n, and
that is, if it is written there, it is experimental condition. These are measured. Once we are flowing fluid through pipes under pressure, right? It's a friction factor. Friction depends. Friction means fluid is touching the side of the pipe. Is not that? So if you recall, it is given there, if I recall properly, it's a velocity to the power n.
yes, sir.
Then it's a matter of surface area it is touching. Is not that? Surface area.
Yes, sir,
so
sir.
It's basically the size of the pipe. Then a little bit temperature because of viscosity. Independent of pressure. Without pressure, even if you are flowing, there is a resistance to flow. Not because of viscosity, that is self condition, but it's because of friction, because of the material contact between material and fluid. Is not that?
Okay, sir.
So that is basic condition to find out how much resistance it is offered per unit surface area of the pipe under different condition. And that's why I gave you a few questions, whether velocity has effect. Velocity means it is change in discharge condition. Do the discharge condition has effect on friction factor? You can find out from these kind of experiments and observations whether it has effect on that. Material is same, pipe diameter is different, discharge characteristics will certainly offer. Reason being, it's a per unit volume of water that is passing through this area. So from there we can answer this kind of question. Is it giving a sense to analyze the query?
Yes, sir. What I was thinking, if the pressure is high or low, then the friction loss will be like it will. How it is not dependent on that?
It's a velocity. First, velocity is there. So velocity and pressure.
Yes, sir.
These are connected. Velocity increases, pressure will decrease. Is not that?
Yes,
you
sir.
increase the quantity. So it's a matter of quantity which is directly connected.
Okay, sir.
That is as well governed by Reynolds number. Means it's a type of flow. Once pressure is increased, automatically it will go towards the turbulent region.
Yes, sir.
Yeah. So that is. Any other? No. Now next it is first to decide the pipeline, a size of the pipe. Now once we have decided the pipe, size of the pipe, it's basically the fitting. Pipes are coming maybe 10 feet or 20 feet in size, single unit. So we need to join them. And again, after joining, it is not the straight line where we need to supply this water. Maybe there are bends, there are some heights or elevation because it's used to supply the water where topography is not plain, it's undulating. So maybe bends are there, joints are there. From the main, if it is connected a sub-main, there may be a T-line joint. T means it is supply one side and two side its outlet. To control the pressure, to maintain the pressure, there are different types of, say, valves. air release valve, flow control valve, pressure control valve. So all these fittings are generating resistance to flow, or they are using or losing. In that way we are losing the head, that is basically energy in the flow system, losing the head. So at the use point, head is reduced. If we are comparing with respect to supply point, at the use point, which is after a certain distance in this pipeline, because of these fittings as well, head is lost. So our idea is to design this whole pipeline supply system in terms of power it is required to pump the desired amount of water through a certain diameter of pipe and required attachments or accessories or joints in the pipeline, how much head will be lost. If we calculate that, then only we can decide, okay, this size of pump should be required to supply water at the use point at this energy level or this head condition. So that is again a question of conveyance system design. So now this is the next experiment to find out the head loss due to fittings in pipe, and these losses in combined is called minor head loss. Means head loss due to fittings in pipe system. So our lab objective for the day is to find out minor head loss. You have learned major head loss, it's a minor head loss for different pipe fittings. And if you recall, head loss due to fittings, that is minor head loss, is simply K, that is head loss coefficient, into velocity square divided by how much? 2G. So here 2G here. This we have already learned in our theory. YB and V1, B1 and V2, I will come into detail. So this is the simple idea to find out the minor head loss coefficient for different pipe fittings. Minor head loss coefficient, why? To find out minor head loss. Basically, if we know the value of minor loss coefficient, then only we can find out what is the head loss, simply by multiplying this coefficient with velocity and using the gravitational force value G. So we can find out this, and in this selection of pump to supply to this here point, we can find out this is the major head loss because of pipes. Here it is fitting somewhere, so it is minor head loss. We can count to find out what is the total pressure available at the outlet. We can have a kind of calculation. So what could be the fittings? Here we have taken 6 fittings. Large bend, sharp bend. What is large bend? Suppose we need to turn this pipeline to 90 degree. We can have a kind of elbow. If you have seen in your household supply system, there is a elbow, very small, changing the direction of pipeline from this to now this. At the same time, there is as well a bigger, means it's a large bend. So elbow it is considered as a small bend. But if you have a larger diameter of this turning, it is large bend. This turning means from here to here, if we are changing, it's larger in size. So it's considered as large bend. So small bend like elbow we have, large bend we have here. To find out the coefficient of head loss coefficient K for these two bends. Then sometimes we need to change the dia of the pipe. Suppose We want to increase the velocity of flow. Certainly we need to reduce the size. So it is contraction, reduction in size. However, if you just reverse this flow, it is a smaller pipe and then sudden it is bigger pipe, velocity will reduce, pressure will increase. So according to our requirement of change in head or velocity, we are changing the pipe from one size to another. So it's contraction or expansion of the size here. So there are two conditions: sudden expansion of the pipe or sudden contraction of the pipe. Then we have number of control valves. So two valves we have taken here, gate valve and globe valve. What is difference? Suppose this is a valve, we have an opener here, and this has a kind of globe which has an opening like this. So by turning this to another side it is solid, just like here, and this side it is opening. So if we are turning this slowly to allow the water to pass through it, this is basically globe valve. It has a valve which has an opening and it is controlled by this opening valve. There is another way of allowing water to move, maybe just like here. We have a kind of plate here as well as here up to this plate here, and it has a certain mechanism to get open this plate. So once this plate is open, water is allowed to pass through this opening. So that is gate valve. It is just like a gate. So two valves, gate valve and globe valve, sudden expansion, sudden contraction, small bend and large bend. These 6 fittings are we have taken for our learning today to find out minor head loss coefficient. Usually major head loss, you know that it's bigger in terms of total head loss, but sometimes suppose there is a system like this where a number of fittings are involved due to certain requirements. This minor head loss due to fittings may be much more than the major head loss. So that is not necessarily always it is less in a system. It depends on system. But if we are thinking about the supply of water in the farm, major head loss is because of friction. However, minor head loss is always because of accessories or fittings. Simple reason, there are less number of fittings with respect to what this is shown in this figure. This is a gate valve kind of thing because it has no oval shape or gate shape, means it's a bulky somewhere in between, but it's a gate. So you can see and immediately understand which type of valve it is. And this is just one pictorial example to show you sudden contraction, means if flow is in this direction, it is reduced in diameter next pipe. So flow is contracted, means increase in velocity and decrease in pressure. However, if it is flowing from this direction, it is sudden expansion of the pipe size. So there will be a loss of head. If we are measuring in between these two sections, we can find out how much head loss is because of this change in pipe size. How much is the head loss because of this valve attachment in the pipeline? We can measure by using a manometer or YouTube manometer usually be used. So here, or this is a large bend kind of arrangement in the pipeline. So we can measure the head loss if we are measuring the head at the inflow point and outflow point of these fittings. So this is basic idea. And theory, if you have gone through already, inflow through a pipe under pressure, head loss is due to friction between the pipe walls and flowing fluid. We have learned earlier that is major head loss, and second is because of head loss due to pipe fitting, that is minor head loss. And we need to measure minor head loss coefficient to estimate the total minor head loss in a pipeline. So this is our objective of the day. Simple idea you have learned in theory as well. Head loss or minor head loss due to pipe fitting is estimated by simply coefficient of minor head loss into velocity square divided by 2g. However, when it is two conditions are there, sudden expansion or sudden contraction if this is flowing in opposite direction, where velocity can be estimated clearly in these two sections, because we have diameter of the pipe D1 and D2. We can find out from the total discharge we have measured. Suppose system is flowing, we are measuring discharge. Usually you have learned in previous two experiments, we have a collection tank which has a graduated sealing basin attachment. We can find out in a particular time, say 15 seconds, what is the head of water that is collected in this tank. So we can find out that volume of water in terms of cubic meter, and divided by this time we can find out what is the discharge. So in this discharge, simply you know that discharge is, if we are dividing by the area, we can get the velocity. So in these two sections we can find out what is the velocity at bigger section and velocity at smaller section or diameter of the pipe. Then we can find out V minus V1 square by 2G. But suppose it's a gate valve, it is simply valve and it has the same size what the pipe size is. So pipe size is usually 25 millimeter and gate valve size is as well 25 millimeter. So there is no change in terms of velocity, but it's affecting because of its safe and its arrangement. There simply we can find out velocity, that is discharge divided by simply cross section area, that is small a, and a is we have taken exactly at the size of the pipe or cross section of the pipe a you can take, that is simply equivalent to V1 minus V2 or V minus V1. So in that way, if we can find out velocity difference because of fitting, we know the value of G. We can measure the head loss because of this fitting by putting a U-tube manometer in this section, both side, inflow and outflow side, and then we can estimate back the value of K. Once we can measure the value of K, simply we can measure the value of head loss in left head loss due to this fitting by using U-tube manometer, left limb, right limb. We can find out what is the head loss in terms of water head. Then discharge we are collecting in a tank of a certain size for a certain time period. We can estimate the difference between tank initial and tank final in time t. We can find out the discharge. In that way we can estimate V minus V1, simply discharge divided by the area of flow for all fittings except expansion and contraction. We can estimate the coefficient of friction because of this fitting or fitting friction fitting coefficient, minor head loss coefficient because of fitting. So this is the simple idea of learning, and finally we need to present our result, the average value of K that is calculated for each fittings, each of the vents and other fittings, and compare to each other, especially sudden expansion, sudden contraction, small bend, large bend, but small bend versus large bend, and then globe valve and gate valve. Then you can compare which one is taking more energy as a loss, and that should be avoided in fitting if we have less head available to operate the system. So this is the simple idea we want to learn today. And finally, you need to also compare your results in graphical form by plotting the graph between discharge and corresponding K value for each of the vents and fittings. So this is our idea. You can see in a system, basically this is another system we have in the lab as well. We have water tank. It is supplied through this pump to all fittings, gate valve, globe valve, sudden expansion, sudden contraction, and then this is elbow. This is sharp bend. This is a large bend you can see here, and both sides we have fitted this pressure measuring attachment to this U-tube manometer here. So this is the simple idea we need to learn in the laboratory today. And for this, I have uploaded a video in your file section. Can you please just see?
Excuse me, sir.
Yeah, please.
Sir, you have sent the mail of 7th experiment to us.
I sent you 7th experiment email.
Yes.
Yes, sir.
Let's take it as.
Okay, okay. So you need this?
Yes, sir.
To write your lab record. Okay, I am uploading this. I did a mistake. So why have you not sent me any mail before that? Reason being you have not seen simply. No? You have not seen my mail. Somebody is telling every time that yes, I have read it. And nobody has replied to my email that you sent the lab write-up for 7th lab. And this is 8th lab. Is not that simple meaning?
Sir, no, sir. We thought maybe the topics would be different. Maybe there was just a mistake. Only after like the classes conducted did we realize that the reports did.
Shruti,
Yes.
Shruti, defending herself or himself, that is very good. I like it. But please don't defend yourself, which is not logically correct. You decided that this is the same topic we are going to do this. Last time, if I sent the same topic, how can be the same topic for this week? Defending is fine. I appreciate defending. We need to prove ourselves correct. But it is not like you are just denying all other things which are correct.
So no, sir, not denying. I agree that I did not read, but I just.
That's why I am asking. The same I am asking. Nobody has read it. That I am telling simply. I ask. I am sending this with a simple idea that at least a few of you will read. But what I learned from here, nobody read it. But anyway, in file section, file upload, I am uploading this file as well, right? And it is here. Files, okay, minor head loss experiment. It is uploaded there. What I sent by mistake, 7th experiment. This is experiment 8 is uploaded there in your file upload section, class material. And there is one video as well, experiment 8, minor head loss, MHL, it is mentioned there. So can you please go through that and then I will give you observations for this lab?
Yes, sir.
Okay. So can you see whether this file means video is opening? I think that is for 18 minutes. 18 minutes. So let us meet at 3:20. It is 2:59. Just watch the video. Bring any query if you have. And then I will give you observations.
Okay, sir.
Okay.
Please check.
Hello, sir.
Yeah.
Yeah, the video is blank actually. The audio is quite working, but the video is
Yes,
blank.
sir.
Yes, sir.
Yes,
Same.
sir.
Same thing
Nothing
happened.
is.
Let me check. But for me, if I am playing, it is. Okay, let me re-upload this. I'm removing this first. Delete. Now, can you please check now? For me, it is working. Can you please check this new video is showing the video as well?
Sir, again, it's
Same
like
issue, sir.
same issue.
Just give some time. Why it is, but it is working for me. Ah, when I uploading, I saw it. It is showing the video as well, but now after closing that, I am running. Can you please check it downloading again?
Yes, sir. Just a minute.
Download it and then run it.
Sir, download is working, sir. Downloaded video.
That is
In Teams,
also
it is not. It is not playing.
So downloaded one is working for me.
that's true for me as well. I don't know why it is creating problem. So it's working now.
No, sir.
The downloaded file is working.
Yes,
That I
sir.
can say. I also see this. I don't know why this problem persists. Earlier it was not a problem.
So for the time being, you can share your screen and show the videos.
But in share point, can you means listen as well?
Yes, sir.
Is it like that? Okay, let me how to share this video. Share point.
Sir, while sharing, we will have an option like include computer sound. We have to enable it first.
While sharing it, I am searching that point only. Including computer sound. Okay. Okay. Got it. So let me share this. Where? Downloads. Can you see this? So now let us understand what are the minor losses
No, sir, we can't. Like, I think if
We can.
you share the entire screen.
pipeline system. We have
Sir, we can hear it.
fittings. Only you can hear that. And a few of fittings here.
Yes, sir.
You cannot see? Mainly there
No,
in any of the pipeline. Cannot see? Let me
no,
show
sir.
you. We have
Sir, we
several
can see download
kind of.
folders, not the video. The my computer folder, we are seeing that screen, sir.
Let me do once again. If it is rectified the problem, remove the file. Upload there. Just wait for 1-2 more minutes. If it is working for new upload, or there is any problem in uploading the file or what? I couldn't understand it. Delete. Upload file. Can you check now?
Now it is working.
It is working now?
Yes, sir.
Yes, sir.
I don't think. But anyway, you just watch
Yes,
for
sir.
next 20 minutes and let me know what you understood or if you have any query, and then I will give you observations. Okay. So now let us understand what are the minor losses once we are supplying water through pipeline system. We have number of fittings and a few of fittings here which are mainly there in any of the pipeline. Let me show you. We have generally a kind of pressure compensating condition, expansion of the pipe, just like here from 25 mm to 50 mm, we have expansion. Then we have contraction. Suppose a bigger diameter pipe we want to reduce to increase the pressure down the line. So it is contraction from 50 mm to 25 mm. Then we have here, you can see two large bend, though it is 90-degree turning, but it's a large bend and it's a very small bend or sharp bend, elbow we can say, but it is also turning to 90-degree. There are two more attachments. One is gate valve, just like here we have a gate, and it is a globe. Globe opening is there, so globe valve. So we have 6 fittings: globe valve, gate valve, expansion, contraction, large bend and small bend in any of the pipeline fitting. So we need to find out what is the minor head loss or head loss because of these of fittings. Major head loss you have already seen, it is because of friction in the pipeline, and minor head loss is because of the fittings. So these 6 fittings, minor head loss we need to find out by the same simple method, by using the head loss which we are measuring by using YouTube manometer. Here you can see we have differential YouTube manometer. So one is connected from supply side and another is discharge side, and the pressure difference in any of these 6 fittings we can measure by these connections here to this YouTube manometer filled with mercury. Okay. Now it is supply of water. Say the discharge and pressure difference in all of these fittings. We have the supply line. Here we have motor and a pump. This is source of water. So this is supply side. Water is supplied to this fitting, and any of these 6 fittings we can operate. We can operate how? It is running parallelly to these 2 lines. So we can operate by these 2 valves. So these 2 valves, either this line or this another valve, another line, and any of the fitting we can measure the pressure difference. What we are doing, we are finding out by using the same head loss due to any of the fitting is equal to simply kV square divided by 2G. So in expansion and contraction only it is V1 square or V1 minus V2 square by 2G we are taking. Otherwise in any of other fitting we are simply getting the velocity of flow. How to find out velocity of flow? Discharge we are measuring per unit time. So discharge rate we can find out from this tank. It has a stilling basin arrangement, and its length and width if we know, we can find out with the depth of flow per unit time what is the discharge from these fittings. By taking the discharge, we can find out what is the velocity by dividing by the area of a particular fitting. And once we know the velocity, we can find out the value of K as head loss, once we have measured, multiplied by 2G divided by B square. So how to find out discharge? We have a tank here. We have a size of this tank 40 centimeter. You can see 40 centimeter or 40.5 centimeter by, here you can see 40 centimeter by 40 centimeter, and depth of water we can find out by this stilling basin arrangement. So here it is scale per unit time. What is the discharge? Now we can find out as volume once we know the area of this tank and depth of water that is flowing per unit time. So let us start first for expansion, then contraction, and then large bend. This first set of unit. Let me show you how it works. So let me open this. The pump is started and this is working. Once it is stabilized, we can see. So this is stabilized and it is collecting the discharge in this tank. So let me see how much discharge per unit time it is collecting. Let us see here. So now this, we should close this valve now, and this is the starting solution, and for 30 seconds let me this is okay. So this is expansion of the pipe. We need to open this supply of water to measure the head by using U-tube manometer. So here it is opening, that is connected to U-tube manometer. Let us see in U-tube manometer how it is. This is the tube which is connected to this manometer arrangement. This is third one, 1, 2, 3, that is connected for expansion condition. So let us open this expansion to supply the head from both sides, and now you can see it's a change in head of this mercury. Measure the pressure difference for the expansion of the pipe fitting. So this is the third, it is opening. So supply line is this side and discharge line is this side. This is the head. Let us see if any entrapped air into the system is there. So we first remove this, and if it is freely flowing without any air, that is, so it is free from any air bubble or entrapped air, so it is working. And now we need to find out what is the head difference by closing these two tabs. So now measuring the pressure difference, here it is from downside, so it is 43 point, you can see it is 43.6 from supply side, from the vertical means ground surface, and this side it is 44.9. You can see 44.9. So difference of these two heads is basically used as head loss once it is converted in head of water in terms of meter, and then you can calculate what is the value of K for expansion. Right. Okay, let us see what it is, means time it is taking from 25 to 10. Okay, 10. Now 5.59, once more. Let me see it. Drain it and wait for we will go this time from 5 to 15. So it is going to the supply, and this is coming from 5 to 15. Now it is, yeah, here 11.7 seconds. Okay, it takes 11.7 seconds to go from 5 to 15, means 10 centimeter filling of this tank requires 11.7 seconds. So let us see what is the pressure difference that is measured by now the contraction. Let us see for contraction side. So we will close this and connect this unit with the contraction side. So close it please. First we need to close it from here. Then open for this expansion line. Both the lines must be open. Yeah. Okay. That is in parallel line. And then we need to find out here, it is the second one. So we need to open the second supply line and discharge line here. Now you can see this is contraction. And to check for any air there, we can bleed it again to check. And okay, no air inside there. So it is working. So we can observe this. So now find out what is the head in contraction side. This side, once it is stabilized, let me see for you. 41.3 supply side, and discharge side it is 47.2, and supply side it is 41.3. Let me see the third large bend. So we need to close this first, connect this YouTube manometer with large bend by closing first to that supply and opening the supply from the large bend side and finding out its connection. That is the first one. So let me connect this to find out what is the head loss because of this large bend of the same size, and this is the head difference we can measure. That is 43.3, 43.3 and 45.2, 43.3, 45.2. So that is for large bend head difference. Now we can use these head differences in supply and discharge side to find out the head loss due to these fittings, and finally finding out the value of coefficient for these. So let us see the remain three fittings. Those are gate valve, globe valve and small bend by given case. So the remain three fittings we can find out the head loss by changing the connection of supply. Simply here supply opening to this line and closing this. This is closed and this line is open fully. So we need to find out what is the head loss for say first small bend, then we will go to gate valve and then finally to globe valve. So let us see, keeping the same discharge condition, and we are taking the same discharge condition here. So keeping the same discharge, we need to measure the head loss because of this fitting from supply to discharge side connection. So let us see first for the small bend here. So let us first connect this small bend, that is called elbow as well in household fittings. So this is connected to this YouTube manometer condition here. So we need to get the supply from a small connection or small gun, sorry. Once it's open, this is the same discharge, so there is no problem of air. So we can find out for the small, then it is 43.2 from the supply side, and discharge side head is 45.3. Now let us see what is the head difference between gate valve. So we need to connect the gate valve. So gate valve connection is here we are given. So gate valve is connected now, and here in YouTube we need to find out what is the head difference in supply and ending side because of gate valve. Yeah. So this is the gate valve condition. It is again 43.567. 43.7, and it is exactly 44.9. 44.89. So we can take 44.8 and 43.7. 43.7, 44.8 or 9 we can take. Now let us see what about the globe valve. So first we need to close this, connect the globe valve. We are now connecting this globe valve. Open it. Globe valve. So globe valve is connected by these two lines to YouTube manometer. Let me see. And this is the line where globe valve is connected. Let me open. You can see that this has a lot of head loss. So head difference is very high in globe valve. You can see these are the conditions. Supply side head is 36.5678. 36.8. Let us get it stabilized. So 36.7, and discharge side it is 51.9 or 52. We can take 52 or 51.9. So 51.9 we can take. So this is the head difference because of globe valve, and keeping the discharge same, we can, means for this particular observation, we can find out what is the value of coefficient K. Because we have measured the head loss due to this fitting from the supply and discharge side by measuring the head loss using YouTube, means different YouTube manometer. So we can find out the value of K coefficient for each of the fitting, and that is our target for this lab.
Sir, I think you are muted.
Yeah. Finished watching video? You finished?
Yes.
Yes, sir.
Yes, sir.
Okay, so I uploaded the observations file, lab observations, to find out the minor head loss coefficient for different pipe fittings. There we have sudden expansion from 25 mm diameter to 50 mm. It is measured mercury level or head basically in YouTube manometer, and discharge that is coming out at that time for a certain time. Here it is measured with respect to the depth in tank. So corresponding time is given. You can find out, estimate what is the discharge in cubic meter per second, or you can change the unit to cubic meter, whatever you like. It could be better. And find out velocity difference to fit into equation. Then it is sudden contraction from 50 to 25 mm. Then it's a large event, 90 degree. Size is the same as pipe size, 25 mm. Sharp bend, that is elbow of same 25 mm size. Then gate valve of size 25 mm and globe valve. So observations are there. You watch the video, you can see it again, how it is measured. You now know. Observations are here and you need to find out the answer. Means minor head loss coefficient you need to estimate for these 6 fittings. Is it okay?
Yes,
Yes.
sir.
Okay.
Yes, sir.
So if you have any other query?
Sir, what was the reason of globe gate to have a high height difference?
It's a shape. Once we are opening it, it offers more resistance. Plate means it's just opening like this. So usually it's a shape which is giving much more resistance to flow. It's a basically shape which is diverting the flow. Once it is open, it is directly passing. But globe has a kind of spherical surface, so it is hitting water first and then going. That is basically it's a shape which generates more resistance, and that requires more head as loss to pass water from it. You can find out more answers for this. It's okay?
Yes, sir.
Okay. Any other query?
No, sir.
Okay. So please complete this experiment and submit by your usual time, that is Saturday midnight. It's okay? And we will meet in theory classes to finish the remaining topics, design of sprinkler irrigation, a few more problem, and then drip irrigation system. Okay?
Okay, sir.
If no query, then you can go.
Thank you.
Okay, welcome.
Thank you, sir.
Welcome.
Thank you, sir. Thank you.